In this video, we're going to begin furthering our discussion of conservative vector fields and line integrals. So at first, let's discuss some curves and regions. These are things that we're just going to have to check off the list to make sure that we can use the theorems in the next following sections. So with curves, so that's C on the left here, if it's closed, so notice here I have closed and not closed, closed, not closed. So you can see the difference there. Closed means it actually repeats, right? It's repetitive. It stays on the same track. C, there's a beginning and an end. Okay, simple. So that's C, right? That's closed for C. For C again, we have simple and not simple. We can see the difference here. The simples on top, these two, don't overlap itself at all. All right, the two curves on the bottom, they intersect each other, have two different points, so that's where they are not simple. Okay, that's a curve. Now, talking about regions, we have two different definitions as well. So take a look here. The weird one first is going to be connected, and then we'll talk not connected. So let's look at those. So what connected means that if I pick any 2 points inside my region, I can connect them by staying inside the region. So take a look here. I have a point there. I can't stay in the region. Same thing here and there. That would be leaving the region, making them not connected. While any point in here, well, you can see that red line kind of showing, that's not it yet, but that'll be the simply connected. Any 2 points in here can be connected, then it's connected. All right, let's take a look at our other definition here. So our other definition is the simply connected definition here. So these two are simply connected, and the two above are not simply connected. Okay, so take a look up here. This curve cannot be contracted to a point. So what does simply connected means? I can take any open region, right? So we wouldn't have a boundary, some region in some space, and if I have that open region, I can contract it down, I can shrink it down, right? It doesn't all go down to a single point, and it's still in R. So as you notice, if we were to try to contract these, let me grab a smaller writing utensil here. If I were contracting, this red line would be coming in, right, at all points, and you can see that it would be stuck around this boundary in R. It wouldn't be able to stay inside of R. So that's what simply connected means. You could see that these, if I put any set inside of R, right? Any set inside of R, I could pick a point inside of there, and I could contract the whole region down to a point. The same thing here, right? Because the space has to be, I can't do a space like this, right? I would have to do some space that is inside of my region and contract it down. Same thing, not simply connected, we have this region here. I can't contract that down to a point in R. So those are our two new definitions. They're going to be checklists for a theorem. All right, so let's remind ourselves what a conservative vector field. Remember, a conservative vector field, we really have the definition. Let me make this bigger again. The definition that if I have a vector field and I have some other function and I took its gradient, took the gradient of that function, I got the vector, that would tell me it was conservative. That was the initial definition. We also have that if it is, we'll have eventually another definition. I almost gave away something, I guess, that we're going to have in a bit. This definition comes from the curl. Remember that if the curl was 0, right? If the curl of my vector field is 0, then it was conservative, right? And these came from that definition of our curl. We talked about that through a video. So this is just a reminder because we're going to have to start showing that our vector fields are conservative. So I wanted to remind you of this is the 3-space definition, and then the 2-space definition is just like the 3-space, but we only have 2 functions to interchange. All right, so let's get into an example of determining if it's conservative or not as a reminder. This book uses this FG, FH, GH stuff. That's going to pop up here and there. I'm going to try to do my best to change it. We're used to doing this like M, N, and P. So if I follow that same definition, I just have to get through each one of these. F, and you could line this up where this is M, N, and P. And if you need to write out that definition, we have it written down somewhere else. But I don't even think about that. I just go through my functions. Okay, M. And if I'm going to do N, then I just flip my variables. This is Y, this is X. That's one of them. Okay, the other one would be, okay, I'm going to pick M, and let's pick P, and I just flip my variables. I put Z under M, and I put X under P because that went with M. And then the last one I have is N goes with P. Do you see I did every single possibility with M, N, and P, and I just flip my variables. Z goes under that because that goes with P. Y goes with that because that goes with them. That's all three definitions there. I don't need this reminder. I can just run through every single one of them, and then I won't get confused by different books using different symbols, because they will. They're going to use FG. Depends on whatever source you look at. Your next class may not even have the same thing. Okay, so let's go through, and we have M, N, and P labeled. Let's find each one of these. Okay, M with respect to Y is going to be, I'm going to go over here and I'm going to drag my stuff over. With respect to Y, the Y is just going to go away here. So this is Z cosine XZ. And now we're questioning, let me move this over. N with respect to X, okay, that's going to be just a Z and then cosine because it changes, and then we keep our XZ. The Z out front came from the chain rule, taking this with respect to X. So that checks out there. All right, the next one we have to do M with respect to Z. Now, unfortunately here, we're going to have to do a product rule. So I'm going to bring this down here. Let me make this a little smaller. Sorry you guys can't do all of this. It's just part of having this iPad. Okay, so let's do M with respect to Z. So I keep derivative of this is going to be a Y times cosine xz, plus I keep my yz, and then I times by, okay, it's with respect to z, so I'm going to get a negative x sine xz. Okay, that's just one side. I'm not going to simplify until I see, and we're working on this one right here. I guess I could put that. Let me move some things around. Here. Okay, and then we're just working on the other side now. This is going to be P with respect to X. Again, that's a product rule. So it's going to be a Y times cosine of XZ plus, okay, then it's going to be, I keep my XY times the, let's just take that out of parentheses, XY times, and then the derivative of cosine XZ with respect to X is going to be negative Z sine XZ. I think that matches the other side. It's very close. Maybe I made a mistake. Oh, no, look, it's kind of confusing here. That X, I was like, oh, that's not Z here, but it's just flipped. So we're good. So that checks out as well. And then, oops, the last thing we have to do is that one. It's remaining over there. Alright, so let's check that out. So we have to do the partial of n with respect to z. That's going to give me a x cosine xz. And then we got to do p with respect to y. The y just goes away because it's only out front. So that one checks out as 2. So that tells me since all those are equal, f is conservative.